So hi, welcome to tutorial 2. Today we're going to talk about logistic regression, which you just heard about in Alex's lecture. We will cover in this tutorial just a brief reminder of the theory, just the supervised learning setting, which you just saw it, so I guess we can go over it very quickly. After that, we'll see an example of binary logistic regression from scratch, which will hopefully give you some like some feel for the problem that you just saw it in the lecture. So now you're going to see it again with a little more data, a little more code. So hopefully it will be more clear. And then we'll see the multi-class case of logistic regression, which you didn't see in the lecture. It's just an extension for logistic regression to the case where there are more than two classes. And I'll mention again that in the end I will talk about the homework assignments today. Okay, so just setting up the environment. Okay, so let's go briefly over just remind ourselves about the supervised learning context. Okay, so in supervised learning we have a data set D of n labeled samples. Here I'm denoting the samples with a superscript I to not confuse ourselves with the elements in the vector. Okay, so it's a little different. So in this context, we have samples in the sample space X. These are also called feature vectors, and we have labels. In the case of classification, the labels are usually a class index or class label. And as you just saw in the lecture, usually the assumption is that there's some kind of joint distribution between the pairs of labeled samples. Okay, so this is the context, and our model is some kind of parameterized function. So, for example, here you can see an hypothesis class called a perceptron. Usually, no markers here, so I can't draw. Okay, so this kind of model is if you have is known as a perceptron. You're gonna see it. It's the most basic building block of the deep neural networks. It's like the artificial neuron. So you have some kind of nonlinear function, and here in affine transform. Okay, so this is an example of a hypothesis class, which is parameterized by parameter vector W and bias B. In the lecture, you saw that W includes the bias term. So usually a perceptron model looks something like, it's drawn like that, where you have parameters W and B, and you have the inputs. Okay, so this is like the artificial neuron in the deep neural networks, and you have layers of these stacked. So training a model is basically updating its parameters, in this case the weight and bias vectors. And models also have hyperparameters, which are not trained. For example, the function phi here is a hyperparameter. We can select various kinds of nonlinear functions. We can have a step function. We can have a step function. We can have a sigmoid function, which we're going to see in logistic regression. Okay, and there are many kinds of hyperparameters that we don't train for them. We cross-validate them. You're going to see that in the homework. So how do you select hyperparameters for model? It's not by training. Okay, so we have a loss function. The empirical loss function is defined over the data set. So usually, as you saw in the lecture, it's the mean of some kind of pointwise loss, which is denoted by L, lowercase l, and usually there's also a regularization term. So we have one term here that's a function of the data set, and one term here which is only a function of the model parameters. Okay, and we wish to find a parameterization that minimizes this kind of loss. Okay, so this is the brief reminder. Any questions about that? Okay, it's a regularization term. It's a penalty that we put in the loss over our parameters. So this is a term in the loss that only depends on the parameters of the model. It's usually added to prevent. Usually we're trying to find a set of parameters that has certain properties. For example, the magnitude of the parameter vector is small, or the parameters are more diffuse, so they don't amplify one specific feature. We're trying to diffuse them over all the features. So usually we add a regularization term because it helps prevent overfitting. You're going to see that a lot. So it's just like briefly right now. Okay, so just like the linear regression context, you just saw it. I'm just showing this here so you can kind of see it in this kind of context. When you have a machine learning problem, usually it's composed of the same kind of building blocks. You have you have some kind of data, which has a domain and a target, like the labels in this case. There's a model that you define. For example, in the linear regression case, you have a linear model. So you have to choose some kind of model and parameterize it. You have a loss function that you need to define. So in the case of linear regression, there's the MSE loss, and you have an optimization scheme. So usually these are the same kind of building blocks in machine learning. So in the case of linear regression, like you just saw, you can actually derive a closed form solution. So you don't really need an optimization scheme, even though you can optimize this various methods if the problem is too big, for example, to invert the matrix. Okay. So let's go over to logistic regression. So again, the same kind of ingredients, but now our model is different. We have not just the linear affine transform. We have a logistic function, which is defined like that. You also saw it right now. And we have a probabilistic interpretation because this function actually transforms the real numbers into the range 0 to 1, which means we can interpret it as a probability. We're going to train our parameters so that we get the right probabilities out of the model. And in the case of the logistic regression, we have a different loss function. Okay, so you saw the cross entropy loss, and Alex explained the kind of logic behind it. So remember, the y's can be either 1 or 0. So if it's 1, and you don't have this term, and then the the inferred y, the y hat, tries to also be 1 to get the loss to 0. Log of 1 is 0. Okay, and in the case of logistic regression, our optimization scheme, since we don't have a closed form solution, but the loss is a convex function, then we can use various kinds of optimization methods, also gradient-based methods. So you're going to see it in a lecture. You're going to see lots of talk about how to optimize loss functions with gradients. I'm just mentioning it briefly because we're going to see a code example that includes that. Okay, so let's look at the logistic function for a second. So this is a very simple implementation of the logistic function, and I want to show you what it looks like. So let's run the code. Hopefully you'll kind of see it. So what I'm plotting here is logistic function. As you can see, it transforms the real numbers to a probability between 0 and 1, or we can interpret it as a probability. Here it has the value half. And this is what the cross entropy loss actually looks like when you take the different cases of y. When y equals 0, okay, so the loss is low when y hat, the inferred variable, is also 0. So you can see what the cross entropy actually does. Okay, so let's look at an example. So we're now going to try to implement binary logistic regression from scratch, just using regular Python NumPy tools, and import a data set from scikit-learn. So scikit-learn is a very, very useful library. Hope you use it. You're going to actually also see it in the homework assignment, and it has a few nice toy data sets which are very small and they're fun to play with. So I just chose one of them and I implemented the binary logistic regression model just on one of them because it has 2 classes. I could have chosen any one of them and just throw away all the labels except for 2 classes, but this will do. So this is a data set of cancer patients. We have 569 samples. Each sample has 30 features. Okay, so each vector x has 30 features in it. And we have two classes. The features are properties of tumor cells that are extracted from images, and we have to identify if the tumor is benign or malignant, so if it's dangerous or not. So I didn't mention, but actually logistic regression is very, very widely used. It's like it's very when you search for it, you see that it's still widely used for various things like weather prediction and spam prediction and stuff like that. So it's not deep learning yet, but it's actually a useful model, even though it's so simple. So hopefully you can see. This is a small code example. So I'm hoping like these kinds of examples will also help you in the homework and understanding what's going on there and doing them. So this is just a simple example that uses sklearn to load a data set. I'm going to run it. What you can see here is that I got a data set that I can get a vector of feature names and target names from that. And I get the X, which is a matrix of all the samples. So you can see X has 569 rows and 30 columns. Okay, so it's a matrix where the rows, so this is X superscript 1, okay? And this is some kind of X superscript I. So this is the ith sample. And for this matrix, we have also a vector Y with the label, which is 0 or 1. Okay? That's the shapes you can see. And you can see the various kind of feature names. These are the names of the features in the data set. So you can see the kind of properties of the cells that they're working with. And these are the target names, like I said. Okay, so this is a simple example of loading data. Just to like show you what it looks like, I'm also loading the data into a kind of a data frame. It's kind of a small font, so it's hard to see. But what I'm doing here, I selected just samples 100 to 109, and I'm just showing like some of the features and the class label just to make it more obvious. Just what you're seeing here is actually what you're seeing there. Okay. Okay. Now we're gonna take our data and split it into a training and test set. So this is an example of how to do that, also using a built-in function in sklearn. So in the homework assignment, you're also going to do this, and you're going to use the training test set splits to do cross-validation to find hyperparameters for your model. Here we're just going to split it, train it on the training set, and then test it on the testing set. Okay. Okay, so now I have two sets of X and Y. I have a matrix, a training matrix, and a testing matrix. And this is about a third of the data. Okay, next step for the machine learning pipeline here, I want to standardize the features. Okay, so for every single feature here the columns is a feature. For example, this is, I don't know, like the cell size. Okay, and this is the cell brightness. So I wanna standardize them. I want all the features to have zero mean and unit variance. So there are no features that have a very, very different dynamic range than other features, because that causes problems for linear models. Okay, so very, very, very simply, I can just use numpy mean, okay, to calculate the mean on the training set. And you can see I have the mean here is 30 element vector. So is the standard deviation, and I can just subtract it and standardize the. Note that I also use the same transform for the test set. Okay. Important. Okay, so let's look at the model. So we're gonna just implement it directly based on the definitions that we saw in the first part of the theory reminder. We're gonna just create a class that uses the kind of a similar API to the logistic regression class in sklearn. You're gonna see that in sklearn all the kind of models have a kind of consistent API that you can use. It's kind of useful if you implement it like that, then you can take your model and do other stuff with it using tools that are in this toolbox. Again, you're gonna see an example of that. So here, just let's look at the code. This is how to implement it in very few lines. Okay, I'm gonna, hopefully you can see, you can't see the bottom part. So I'm gonna start at the top. So this is our logistic regression model. We have a predict probability function. So these are the names that if you go to the logistic regression in sklearn, then you can see these exact same functions. So this is like kind of trying to show you what's happening behind the scenes in these kind of toolboxes. Obviously, this is very simplified, but you can see it's basically what you expect. You have kind of a dot. You're basically multiplying the samples by the weights. This is the weight parameters, and applying the logistic function. Okay, remember that our model is the logistic function of W transpose X plus B. So here we're actually just adding the bias term, creating XB, which is this matrix, just adding ones here. Okay, adding ones here, so we don't have this affine term. We just have this. Okay, because it's easier to derive the gradient from that. So this is the probability. Remember that the output here is a probability of the sample being equal to the class 1. Okay, that's the interpretation. So if you want 0, then it's 1 minus that. And our predict function, which should return not a probability but a class label 0 or 1, is simply just calculating the probability and then checking whether it's greater than half. Okay, so we're going to select the class with the highest probability. So this is like how it looks like in code. Okay. Now to fit the model, actually, how do you train the model to fit the data? So as you remember, there's no closed form expression that you can use if you have a data matrix and you have a logistic regression model. You need to train it using some kind of optimization scheme. So here, what I implemented is a very basic gradient descent. I just calculated the gradient of the loss with respect to the parameters. So remember, the loss is a cross entropy loss, so it's this kind of thing. Hopefully that's they wrote it clear. So I'm not gonna derive it now, but if you want to just apply some calculus and you say that y hat is sigma of W transpose X plus B. Okay, and this is a function that's 1 over 1 plus e to the minus z. So all these things that you can just calculate the derivatives yourselves and have fun doing calculus, and you can validate that I did it correctly, even though it was late at night. So I'm gonna kind of decrease the font, but what's happening here is basically we're going over the whole data set, some kind of specific fixed number of iterations. Again, this is a very simple scheme. It's not how you should probably do it, especially not for deep models. Okay, so the forward pass is just taking the whole data set, predicting the probabilities, y hat, calculating the loss, so that you can see this is the binary cross entropy term right here. Okay, and this row here is where the kind of the training happens. So I'm just calculating the gradient. Okay, so what you see is written here. It's X transpose, okay, times the y hat minus y. Okay, so 1 over n. Well, 1 over n doesn't matter. So basically, if you spend some time doing calculus, you can get to kind of this kind of term. So this is this term is the derivative of L with respect to the weight parameters. So we don't have a bias term anymore, so we just have the W parameters. So when you derive it with respect to the parameters, you get this. Okay, so you're going to see in a lecture that when you take kind of a gradient and subtract it from the parameters, you converge to kind of some kind of minimum. If it's a convex function, then you can actually optimize it globally. I can give you some kind of brief intuition, just like a preview for the lecture. If you, let's say we have one parameter, okay, we have one parameter w, that's it, not a vector, and we have a loss, which is a function of w, so the loss looks somehow, okay? And if we're here, if we're somewhere along this loss, you can imagine that the gradient will, actually the gradient is up, but if you go negative gradient, then you're going down. So if it's not a convex function, you may find yourself in some kind of local minimum. But lucky for us, the binary cross entropy is a nice function to optimize. So if you want to calculate gradients, then you can have fun. So this is how to do it manually. Again, in the homework assignment, you will do it manually for another loss function, because it's good practice to do it and then implement it and see if it actually converges to something. Okay. So now I'm fitting the model. So I took my logistic regression class here. I said I want to run for 1,000 iterations with a learning rate. I gave it my scaled training set. Okay, and this is the loss that I got per iteration. So as you can see, it really does converge. The loss goes down, which is good. And now predicting for the test set, we get a very, very high accuracy. So don't expect this kind of accuracy in real problems. This is a very, very small data set. It's a toy data set. And there's not even a regularization term here. So it's kind of it's an amazing result, but it's fun to use like the toy data sets in sklearn to do kind of small implementations like this. Okay. So that was an implementation of the binary cross entropy that you saw in the lecture. Hopefully it's a little more clear now what it does and how it does it. Okay, it's just so small notes about the implementation. So it's not really a good idea to run for a fixed number of iterations. Can anybody think why? Why it's not a good idea? Why not? Okay, so I can kind of, what would happen if I run too many iterations? So like I should have stopped earlier. Mm-hmm. Yeah, you can overfit because if you stopped earlier, you may have found a parameterization that generalizes better to the training set. If you keep running, okay, you might go. You may be keeping you may keep with the optimization and your loss may go down, but you might be overfitting. So it's not really a good idea to run for a fixed number of iterations. A better idea is to use early stopping and use the test set in the middle. So just see what happens to the actual test error, which you care about, not the training error. Okay, and another thing in this implementation that it takes the whole data set and computes the gradient of that. So that's also not a very clever idea. With real data sets, they're going to be really big, and usually you run on batches. You don't take the whole data set and try to compute the gradient of the whole thing. Usually you can't even fit the whole thing in memory. So okay, and like I said, the whole cross entropy gradient, you can try it yourself and see if you get the same result. If not, then you'll have fun in the homework assignment calculating some other gradient. Okay. Right. So now the multi-class case. So basically, what we saw now, the logistic regression, it was nice. We took some kind of a sigmoid function and we said this is the probability of the class 1. Okay, and we had two classes, so we said the probability of the other class is 1 minus that. So what if we have more than two classes? So what if we want to use this to classify to multiple classes? Let's say we have images and we want to have dogs, cats, and sheep. Okay, so what do we do then? Not that this is a good model for image classification, but so any ideas? Okay. So what would you do for 1 versus all? Okay. That's an excellent answer because it's exactly the what's written here in my slide. So yeah, you can basically train classifiers, but what's the drawback from that? Okay, but the more like a direct problem is that there's nothing constraining the different classifiers together. So you don't really get a probability distribution. You don't say like this sample is 50% dog and I don't know 30% cat and 20% sheep or whatever. You can get kind of strange strange probabilities that don't really make sense as a joint distribution of the classes. So that's not so great. So what we do, we define the softmax function, which is a nice function. It allows you to create a probability distribution based on scores. So what are class scores? Class scores are just when you take kind of this transform, so it gives you some kind of score per class. I'll show you the next slide. And the softmax function, it just what it does, you have here an element-wise exponent of this vector z, and here you divide by the sum of elements in the vector. So note that this function is vector valued, meaning it returns a vector, and it's a function of a vector. It has multiple variables. Okay, so basically you take a vector and you exponent all the elements, and then you divide by the sum. So what you get is a vector with elements in 0, 1 that all sum to 1. So you can think about it. You can think about it like it's class probabilities. Like each element in the vector is a probability of a different class. Okay, so now the model. So instead of logistic regression as you saw it here, our multiclass extension will look like that. Now notice that we have a matrix W instead of a vector W. Okay. So as it says here, try to draw it kind of out of space. So the example here is a single sample. So you have a sample X, okay? You have a sample X. This is a single sample, and your W is now a matrix. Okay, so X is D, right, on 1, and you're basically transforming it to with W to the to the class score, okay, for each of the classes. Hope it's clear from this. Well, in this case, then it will just be 2. So you have like 2 elements here. Okay, so yeah, you can, like in the previous case. But in this kind of extension, then if you have 2 classes, then W will have 2 columns. It would look like that. Okay, it would look like that. So when you do WX, okay, then you get kind of the class scores. So this is the score for each class per sample. So you get. Hope it's clear. Just look at like the dimensions and you'll see it turns out. Okay, so now the probabilistic interpretation, since we took the softmax, is that each element in the y hat is the probability that given the sample X, it belongs to the class J. So the jth element here, for example, this one is the probability of the second class. Okay, J equals 1. That's the whole idea. Okay, so you can see why it's an extension. But now our labels are not so good because originally our labels were just, we had labels that are belonging to the set 0 c minus 1. Okay, so just integers, but we're trying to compare them to one of these vectors, to a probability vector. Okay, so instead of our regular labels, what we're going to do, we're going to define what's called a Onehot vector, which means it's just a vector with all zeros and 1 in some component. So if the ith label, okay, so yi, this is the ith label. If it was j, class j, then simply we create a vector with 1 in the jth component. So if we think about, like, this is our ideal softmax output, so it's like a singleton distribution. Like, it has all the weight of the distribution on a single component. So we're trying to get our softmax to move all the probability for the sample I to the specific component in the vector. Okay, so again, now we need a loss function. So we again use the cross entropy loss, and it's really the same thing, because remember that now this is a Onehot vector and this is a softmax output. So basically this is all zeros except one of the components. Okay, and then it selects that component from y, and it wants that log to also be 1. Okay, it's really exactly the same as the softmax. So this is like the the multiclass softmax, cross entropy, sorry. Okay, so like I said, it's trying to to move it towards a singleton distribution. Okay, so now let's look at a code example. Okay, so this time our data set will be a data set of handwritten digits. This is known as MNIST. It's very, very famous. It used to be like very, very widely used in machine learning papers. Like, people used to publish, and now it's just considered a toy data set because for a long time now, deep learning models just get extreme results on this data set. But you can see that we're going to get good results even with multi-class logistic regression. But what's nice, you're going to also implement in the homework a different kind of classifier on MNIST, and you can compare the different implementations. Okay, so now we're going to do it with PiTorch, not with NumPy and Scalearn. But I'm going to just show you like very, very basic stuff, just using the tensors in PiTorch and using the data loading classes, because again, that's what you're going to see in the homework one, and when you'll need it in the second homework, you'll see the more advanced kind of model building capabilities in PiTorch. Okay, so this code sample, what it does, it loads the MNIST data set. So this is what it looks like. Probably you've seen these handwritten digits somewhere. It's very, very famous. So this is like the 10 first samples. The size of the data set is 60,000 images. Each image is 28 by 28, and it's a grayscale, so it has one channel. And I'll just go over this kind of code example briefly. You have in one of the packages in PiTorch is called Torch Vision. You have built-in data sets similar to what I showed you with sklearn, but here it downloads it from the web because it's kind of large. So you basically, when you run this, it downloads the MNIST data set for you, the training set, and then you can wrap it in a data loader, which is a class that lazily loads batches of data from disk to memory. So you can control, for example, the batch size. Like, you can say, like here I said, I want to, in each batch, load 128 images to memory, and what it does is it takes care for you for all, it takes care for all the loading. From your perspective, it's like the whole data set is there, and you just get batches from it. Yeah. in the homework, specifically, each question will use something else, and you'll need to use what's in the question, because it's like some of the code is already written and you have to complete it. So it's kind of, you can theoretically, it will be harder. Some of the code in the homework assignment is based on PiTorch tensors and some is not. It's trying to diversify you to like know various things, because everything is very useful. It's kind of a hands-on course. Okay, so just same idea here. This is the training set, this test set, and this is just a utility that plots some of the images. Okay, so we loaded the MNIST data set. Okay, so this time what we're gonna do is implement it with PiTorch tensors, not NumPy tensors. Like I said, they're very similar, just PiTorch allows you to also put the tensor storage on the GPU. And an important feature of PiTorch, which is going to be very useful for training deep models, which you can't easily use calculus to create the gradient of the loss for, is the autograd feature, which is an important feature that automatically calculates the gradients for you. After you can create an arbitrary loss function that has an arbitrary deep chain of calculations, and AutoGrad will just track all the calculations and then calculate the gradient for you. So, yeah. No, it's analytically. It's not numerically. Yeah. Every function there, it defines its own gradient. So if there's an exponent, then it defines like the gradient of that. So it's analytic. It's not numeric. Okay, so we're not gonna like go into AutoGrad now because it's not necessary. I'm just telling you that, and you're gonna see like an example of how it's used, and you're gonna see that I'm not calculating the gradient anymore manually. I'm just saying I want gradients, and give me the gradients, and then using that to optimize the model. Okay, so now I'm gonna break down like the model implementation to a bunch of functions. These functions are implemented just with PiTorch tensors, very similar to NumPy. Not very interesting here. So this is the implementation of the Softmax. There's a small numeric trick here, but it's not also very interesting. The core of the thing is just exponent of the input and then divide by the sum. That's the core. The other stuff is just so it's numerically stable. Cross entropy. Okay, this is again the multiclass case like you saw previously. So, but an important thing to note here is that we're working on batches of data now. Okay, it's a batch. So you have n is like the batch size here. So z is the in this case the wx. Okay, so you have the batch size samples and the scores, the class scores, C. So the softmax here will do a softmax of each row. Okay, it does a softmax each row. That's why we're working on the first dimension. So dim1 means work this way, work on columns. Okay, this is the rows are the dimension 0 and dimension 1 of the column. It's similar to NumPy. And same for the cross entropy. Here the y's are the same dimensions, but these are the probabilities, and these are the class scores. The z's are the class scores, and y is the probability. So y is after softmax, and z is before softmax. Okay, so now the optimize. Here, optimizer is a different function. I specifically broke it down like this because you can see. Again, when you use PiTorch more and you're going to train bigger models, you're going to see that it's very helpful to split the whole thing to different kinds of things that you can change and switch around. You can try a model with a different kind of optimizer, or the same model and optimizer but change the loss function. So this is just like a preview for that. So basically here, this optimizer, what it does, it gets params. So params is a list or a tuple with the weight matrix and the bias vector. Okay, and you can see that the params somehow has a grad, and what it does is takes the grad and the learning rate and subtracts it from the param values. What you saw before is that I calculated the grad and did the same thing. Okay, so I'm gonna show you soon where the grad comes from, or at least how you request it. And this is just a small function that I need to create the Onehot vectors from the class labels. Yeah. Oh yeah, it zeros the gradients because otherwise they will accumulate between. When you yeah, in a few slides you're gonna see the training loop. So. Sometimes you do accumulate it, sometimes it makes sense, but usually between batches you have to zero it. Okay, so this is the model now. The model now is basically just a container for the parameters. So our parameters, W, this is the matrix, and this is the vector, bias vector. We initialize them to normal random values. We have n features and n classes. So the features are the number of features in X, and this is the number of classes. And we specify, when we create this tensor of random values, we specify that requires grad is true. What that means is that every calculation you do with the tensor, for example, if you take the tensor and multiply it by 2, then it remembers that it was multiplied by 2, and it can calculate the gradient of that with respect to that tensor. So the gradient can be calculated backwards, which is known as the backward pass when you train deep networks. You're going to see that in the next lecture. I'm just saying it now because we're going to need it to implement. Okay, so this is just telling PiTorch that I want to compute gradients. I don't want to do it myself this time. And forward is just take the matrix of samples. This is a batch of samples, and pass it through the model. So here we're doing the affine transform. Okay, X matrix multiply with W plus bias vector and put it in the softmax, and then we get the probability of each class. Okay. Okay, so now the final parts are, let's use the model. So here's a function that evaluates the model on some set. So data loader is what I said, the class that gives you batches of data. So this is the function that I'm going to use to evaluate on a test set. Okay, so what it does, it runs. It iterates over batches from the data loader. So you get X here and Y are batches. For example, 128 samples. It takes each image and creates a column vector. And then it passes it through the model to get probabilities. Okay, to get this. Then the prediction is the class label. Okay, so it takes the maximum value from each of these. It takes the maximum value as the prediction. So if the maximum value is in the jth component, then we predict it's class J. Okay, and then we just sum the number of correct predictions compared to Y, which is our actual ground truth labels. That's how it works, really simple. So let's run it on the test set, and we have an error, obviously. Should have run my model. Okay, so I run it on test set, and I get, let's run it a few times. I'm getting 11%, 12% accuracy. Any idea why I'm getting these numbers? Why am I getting kind of numbers around 10%? Yeah, who said that? Exactly, we have 10 classes. Right now the model is initialized to random weights. Okay, so this is a nice sanity check with a random initialization, and I have batches of data with 10 classes, so it's a random guess. Okay, so my accuracy is 10%, around 10%. Okay, every time I run this code, I'm creating a new model with a different parameterization, and I'm running over the test set, and I'm seeing that I'm getting around 10% accuracy. So this is a good test of if I implemented everything correctly. At least not everything, but some of the things. Okay, so this is the final part. Let's run it while I talk because it takes a few seconds to run. So this is the training loop. Training loop is a kind of pattern you're gonna see again and again when you work in this course and other kind of machine learning tasks. So usually we divide our training to epochs. So an epoch is an iteration over the entire data set. So like I said, we have in MNIST, for example, 60,000 images, but we're dividing them into batches. Okay, so let's say my batch size is 1,000, so I have 60 batches in each epoch. Okay. So here I'm saying I want to run for 5 epochs. I want to run over my whole data set 5 times. In each epoch, I'm running over my training set. This is the training data loader. So each time I'm I'm getting samples from my data loader, I have a batch for, say, 1,000 samples. I'm using those 1,000 samples through my model to get the probabilities, and using the cross entropy loss to see how well my model is with the current parameters. So I'm taking this loss, and now's the kind of PiTorch autograd magic, the backward function. Okay, so the backward function, what it does is it starts going, basically it's doing this. It's saying I have a loss, and I want to calculate the gradient of the loss with respect to W and B, which are the only 2 tensors that I defined with required grad equals true. So I have 2 tensors with required grad equals true. Those tensors went through a lot of calculations until this point where we got to the loss. So it's like a function of a function of a function. And basically it just goes back with the chain rule and calculates the gradient of the loss with respect to all the tensors that we requested requires grade equals true. So the whole back propagation thing, you're going to see it in the lectures. But basically what this does, when I say this, it goes backward and it populates the grad field that you saw in the optimizer. There was a grad field, and I used the grad field to update the parameters. So this is what's going to make the grad field have a value. After this, it has a value. That's why after the backward pass, you could call the optimizer, give him the parameters and the learning rate, and it will update the parameters for you. So after I did the forward pass and the backward pass, I now have new parameter values. Okay, so after each batch, I'm updating my parameters once. Okay, and after I'm done with all my batches for this epoch, I'm evaluating my model. I'm checking how well my model is right now. Okay, and then I can decide, I didn't implement it here, but I can decide if I want to stop or keep going for another epoch. Okay, and hopefully the loss will go down and the accuracy will go up. So I'm printing here after each epoch, and yes, you can see we eventually, after 5 epochs, we reach around 90% accuracy on both sets, which is pretty good for a very, very basic model and a toy data set of handwritten digits. Okay, and this is a very basic implementation. There's not even any kind of regularization here, anything. It's very, very simple. No, if it's not, the question was if the batches need to create a yeah, like you said, if the whole set size must be divisible by the batch size, so you don't get a small batch in the end or something like that. No, it's not a requirement. You can get a small batch in the end, and so what? There's nothing in the code that prevents it. In some cases, you may have a problem with a specific feature in your model or something like that. But in this case, nothing here cares. It just changes the number of rows, basically. That's it. Okay. So just final notes here about this implementation. So it's not a good implementation of multiclass regression. If you want a good one, then you can see like how the libraries do it, but it's good because I didn't use anything except tensors basically and the autograd, but I showed you how to do it without autograd before. So basically, for example, in PiTorch you get lots of stuff for free. You have You have a perceptron fully connected layer, so you don't need to implement the affine transform, and you get a softmax function, so you don't need to implement that. You don't need to think about how to make it numerically stable. And you have an SGD, stochastic gradient descent optimizer, and many other optimizers. And you have cross entropy loss and lots of other loss functions. So you have everything for free. But this kind of very basic, simple implementation kind of shows you how stuff works behind the scenes. So it's like good for an intuitive understanding, at least now, because later on you won't be able to do it like so low level when you do like larger models. Okay, so that's it.